Yeah, so some background. Been kind of doing the Tidyverse stuff. We covered ggplot already, and there's been lots of requests to cover the other components of Tidyverse. So Tidyverse, let's just get some background in here. So stole these definitions from Wikipedia, is really aimed at data science. So data science is just kind of a catch-all phrase for basically working with lots of data nowadays as computers have enabled. So lots of statistics and scientific methods, algorithms. And a big component of data science is what they call data wrangling, also known as data munging. And that's basically you get in your data and your data is unfortunately a mess. So you have to do a whole bunch of work to get it into a form that's usable to yourself. And Wikipedia, anyways, claims that data analysis typically actually spend the majority of their time in the data wrangling state compared to the actual analysis. So that's where the Tidyverse packages come in. It's for R. I know Python is the thing everybody loves now. It's got lots of libraries and stuff, but R was sort of the initial statistics languages. Well, I guess S+ was actually, and then R was the open source or the free implementation of that. And there's been this group of people, starting with Haley Wickham, I think his name is, who built up this sort of opinionated, they call it, collection of R packages that are tightly coupled together, and they have the same underlying design philosophy, grammar, and data structure. So they all work really nice together. And the main set is Tidyverse, but there's a whole bunch of other ones that have built upon these ideas. If you look at Tidy, there's like I saw Tidy Text and a bunch of other ones that are kind of like it, but the main branch is the Tidyverse. And I've given you the link there, and you just import the library Tidyverse, and then that sucks in all the sub packages. So let's just have a quick look at what the Tidyverse is. So if we go over to the tidyverse.org website, here is the main packages. Actually, for whatever reason, this compacts down. I don't think that's very good. You have to blow it up to full screen, and then you see these additional two in the middle. So you have dplyr, ggplot, which we have talked about before, so we won't be talking about that in this one. Forcats, tibble, readr, stringr, tidyr, and purr. And then when you're on this website, you can click on any of them. So for example, let's start with readr. And it tells you a bit about it here. It's got a getting started guide. It's got these great cheat sheets. All of them have cheat sheets. So if you click on the cheat sheet, it'll bring up a big printout you can make that covers the primary operation. So that's a great way to get an overview and put it on your, print it out and keep it with you. And then they've got the main part here is, so they have a kind of a review and an example. They got some articles written about them, but the one I like is the reference tab, which then just has all the functions. So one of the functions we'll be using is read TSV. If you click on that, that's got all the details about it. So I always find I have quite a few Tidyverse tabs open in my browser as I work along. We'll just close that. And as I say, you can bring it all in with the library Tidyverse. So I've got an Emacs session here with R running in it. So we'll start that up here. We'll just compress Control-C, Control-C, and Emacs will run the command. So here I've just ran the library Tidyverse. It runs over here, and you can see it's brought in a series of packages. And it warns me that it's overriding my stats filter, and my stats leg have been overrode by the dplyr versions. So these are the packages there. So we got dplyr, which is a grammar of data manipulation. We got ggplot, which is for decorative creating graphics, which we've talked about before. We got forcats that basically just cleans up factors in R a bunch. So factors are basically, if you will, enums. So you take strings and you assign them numbers instead, and then that's handled transparently in the background. That can speed a lot of stuff up. especially comparison and things like that. So you got tibbles, which is the data frame, the R data frame reimagined and modernized. You got readr, which provides fast and friendly ways to read and write rectangular data from delimited files, such as tab separated files and comma separated values and stuff like that. You got stringr, which is a cohesive set of functions to make working with strings easier. So again, this is, I mean, you have a lot of this functionality in R already, but these packages take that functionality and they make it all have a common interface and play very well together. And that's really the power of the Tidyverse. You have Tidyr, which helps you create tidy data. So there's a whole, there's a book about Tidyverse written by the people data science, and they explain what tidy is. It relates back to the basic rules of database management. So you can look into that. And then you have purr, which enhances R's functional programming toolkit. So now, to give an overview of this stuff here, you could probably do a whole thing on each of these, but I thought maybe we'll just do a fairly involved sample and we'll run lots of these functions and hopefully you'll get a lot better feel for what them is. There's no way to learn them, besides actually using them. So keeping with the, I needed an example, so I picked an example that I happened to be interested in, which was that there's this Navigation Canada publishes this thing called the Canadian Flight Supplement, which I have open on my right here. And basically, we just scroll through this a bit. It has all the little aerodomes and big aerodomes. So an aerodome is like an airport, except for an airport has to have fire facilities and stuff like that. So an aerodome is just basically somewhere you can land and take off in Ontario. And it's got information about, so here's like the coordinates, who the operator is, what to contact when you're flying in and stuff like that. So all these sort of details, and they provide an electronic subscription and you can have that, but sometimes it's nice to be able to do some analysis on this. So I decided to see if I could, by data wrangling, re-extract all the information out of this. So there's a lot of implied structure to this data that is visual and it's implied in the layout, but it's all locked inside a PDF. So first I tried PDF to text, which just converts PDF files into text, but it was not able to handle the structuring here. Like, for example, it would think that FIC and London is all one line because, it doesn't realize there's a breaker here and the ones on the left are headers, and it doesn't recognize if they wrap halfway through the page. And so it just does a really bad job. But you can run PDF to text in TSV mode. And when you do that, I can just do that in my prompt here. PDF to text. So PDF to text is part of the Poplar Utils library. And there's actually, Poplar has a library for R and Python and stuff too, so you can run it directly. So PDF to text. And if I run TSV mode and I run it on this PDF file, it basically just goes through it and it'll make an output text file. So now I can load that up. ECFS English text file. It's really large. And then it's basically got for every, we go in here, every word. So here we see this word CFS, digital edition, caution, right? That's all the stuff off here. CFS, digital edition, caution. And then it has the bounding boxes here. So you can see there is left, top, width, height. It's got what it thinks are the page numbers are accurate, of course. It tries to break stuff into paragraphs and blocks and lines. But as I said, it works great if you're trying to do something like an ebook or something, right? But due to the layout of this sort of information, it doesn't do a good job there. So that's a good exercise for the Tidyverse to see how nicely it is to clean this up. So let's get started here. So the first thing we're going to use is the read TSV function. Read TSV is from the readr package in Tidyverse, and it just reads tab separated value files into the tibbles, where the tibble is the new data frame, if you will. So I'm going to just close that out there. We'll close that out and we'll give this a try. So first I'm going to set my width to 256 to stop these, so we can see the full tables. That's just an R option. So we'll do this, and then we'll run this input command. There we go. And then I'll ask to see the input. And you can see this is the, basically it's sucked in that tab separated value. You can sort of see the output. It tells me what each of the columns are. It tells me what types it's inferred for them. And that's it. So the tibbles have a nicer printing functionality than the data frame. You can see that you can set like the precision. So my precision is set to 3 digits by default. It'll handle, if it goes off the screen, it does a nice job on suppressing columns and telling you which columns it's pressed, and it just prints out a little summary of the page. Now we've also used in this example, actually, we haven't used in this example yet. I've mentioned this quotation operator. So we'll get back to that on the next one. That I put that too early. We have our first of our string functions too. We have strc, which joins strings. And of course, you already have a R function to join string, but these are vector functions, so they join strings in a vector format. So for example, if I have two sort of vectors. So this is an element-wise join. You can see it's joined this with high and that with there. So that's, and having a vectorized string join function plays very well with working with these columns where we want to do the same operation. We want to do operations row-wise, right? So we've joined this, and the first row has joined and the second row has joined. So that's an example. I mean, R has that and you can implement that, but it's just nice to have it all in those functions. So as I mentioned, the PDF to text input has a lot of stuff here. It's got some control stuff where it figures out where pages start and flows and lines and stuff like that. It's got those all marked by these conf -1. So the actual text is just the ones we want. Here's the 100s. And it's got, of course, the left and the left spot here and the top spot and the width and the height, which are kind of cumbersome ways. So we want to just replace that with computing the bounding box. So that's what this does. So we take the input, which is what we read in the previous one here. And here we see this pipe operation. So the pipe operation, actually, all it does is it takes the thing that's on the left-hand side and it applies it as the first argument to the thing that's on the right-hand side. So if we actually look up the mutate command, so let's just bring up the help on that. You can see mutate, the first thing it takes is the data. So basically, this pipe symbol lets me take the first argument and write it above. And that seems maybe kind of trivial and silly, but it really avoids a huge, ugly nesting of brackets. And it also makes it read naturally to us, right? To read it otherwise, you have to start at the innermost argument and read your way from the inside to the outside, which is not a natural way to write this. Like I could compose these all. So select, the first argument of select would be filter. The first argument of filter would be mutate. The first argument of mutate would be input. So I'm already like 3 levels into the programming, and over here somewhere in my margins, if I wrote this all out. But by using this pipe operation, it just forms naturally. You think, okay, input goes into mutate, and then the results of that goes into filter, and then the results of that go into select. So that's just one of these examples of these really nice things that makes your life a lot better. So basically we mutate does not actually mutate the table as in input remains unchanged. I mean, I assign to it, but it computes a new table with these new values in it. So we take x0 is the left, y0 is the top, x1 of course is the left plus the width, y1 is the top plus the height. And then we filter them. So we want only lines where conf equals 100. So that's our actual text. And then I want to get rid of, you can see this big text in here. Let me just grab my text here. So we got this, oops. This is the sample file. So we have, let me pick my pen there. We basically have this stuff here I would like to get rid of. Easy way to get rid of that is it's just big text, really big text. So we take the width times the height of the text here, and we divide it by the number of characters. Kind of gives us the ideal size of an individual character. And basically, we only want ones that are between 3 points by 3 points by 72 points by 72 points divided by 4. So a point is an inch. So basically anything that's between each character is between a 1/4 inch and some really small values, because as if like the first time I just cut out the really large ones, and then at some point I'm like, hey, why is this? I'm getting these little bits of garbage, and it turns out there's little pieces of text in here that I don't know, maybe it's done in a word processor or something that you don't really see, but they come through. They got some. They're just absolutely tiny. So that's why a human hasn't noticed they're still in the documents. And that's the typical of the data wrangling, right? It's all this painful stuff that you have to eventually fix. So yeah, so just these lines, just the sort of reasonable size text. And then I didn't really like some of these headings here. So out of the results here, I want the page number, but I want to call it page. And then I want Y0, Y1, the width, the height, and the text. So we can run these lines here and see what they do. Have a look at this table here. So you can see that has cleaned up my table. As I said, it's pulled out the page, the Y0, Y1, X1 width, height. And if we actually dug through it, we'd see in the original one, there was like single letters E and combined letters M and P and stuff like that from the sample here scattered randomly throughout, and those are gone now too. So I've talked about mutate, talked about filter. String length, again, is a function that computes the length of a string, and what's nice about it is it's vectorized. So how these actually work here, if we look at these mutate, it's something they call the tidy evaluation. So these are expressions, but mutate evaluates them in the environment of the table. So it substitutes when it takes these expressions here, and then it extends the current environment, your current variables with the variables that are in the table in vector format. So inside this mutate, x0 is assigned to this vector here, this column, and x1 is assigned to this column. And then it evaluates these expressions in that context. And that's nice. That lets you refer to these variables. And basically, if it's not in the table, then it falls back to the sort of global, the scope of the surrounding environment. So I can also refer to stuff that I've defined in my R programming. They call that data masking, where your data values mask whatever is in your upper level environment. All right, so let's have a look at the next page here. So this document actually is roughly 899 pages long. Sorry, exactly, roughly 900 pages. And only the first half of it is actually these aerodome items. It's got stuff we don't care about, like these title pages and blank pages. And at the back, it's got a massive reference on what everything means. But we just want to get these pages. So we could just, do it once here and figure out what pages they are manually and put in a page room. But that wouldn't be very generic and it wouldn't work with the next version. So we wanted to split them. And the way decided to do that was to just extract the header. So if we go across the top here, We can easily split some of this information here. Each of the pages has a header region that tells you what it's about. So you can check this here, and roughly this line occurs about 37 points down from the top. In PDF coordinates, you measure everything from the upper left-hand corner. So basically, we just take the input and we filter it. So we want everything where y1, which is the bottom part of the text, is less than or equal to our split point. And that'll pull off the headers. And so that splits them out into headers. So let's run that and you can see. So if we have a look at headers, now we have this information here. You can see it right from the top, Canadian Flight Supplement, blah, 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 December. And if we printed more lines, we'd see that's all that's in there. And then we want to remove that from our pages too, from our general input, which we'll work on processing later. So how do we do that? We can do something called an anti-join. So that's a dplyr command. And basically, you've got these joins which combine tables. And if you remember right, I said input becomes the first argument. So this is actually anti-join input comma headers. So that does a join between input and headers, and join merges the rows in some way. And the way it does that is it looks for the columns that match up at the top. So if both tables have a column called page, then it'll say, okay, we need page to be the same value. And what the anti-join does is it takes the left columns that have no matches in the right-hand side. So because we pulled this out of it, when we anti-join it with it, we're basically doing the intersection with the complement, if you will, and we will extract out from input anything that's in headers. So we can run that. Have a look at our input. And you can see the input, well, the input still has all the first page information here, but if we printed out more lines of it, which we can do here, so let's do that for print input. We'll print the first, let's say 50 lines of input. Oh, and that's still not enough to get through the first page. Anyway, so hopefully you'll just take my word for that. We'll see later that it is actually indeed gone. Okay, so now we've got the headers pulled off the top, and let's move on to my next page here. What we want to do is we want to look, basically we want to look for the ones that say Aerodrome Facility Directory in the upper right-hand side. Those are the headers we want. Like if we jump down to say page 500 here, we can see we're in section General A7, and this is definitely not the sort of information we want. So we want to extract all the pages that have Aerodrome Facility Directory in the top. So how do we do that? Because if we look at our current set of headers, it's just a bunch of words. Fortunately, it's not too terribly difficult. So we take our headers, we arrange them by page and the Y location. So arrange just sorts them, if you will. And they're probably already arranged by page and Y1 location, but do it to make sure. Actually, I can see they're not here looking through. We got Y1's 15.7, 16.2. And then on the same page, we go back to 15.6. So basically that sorts them by page, and then within the page, they're where the bottom of each block of text is. And then we group them by page. So that puts all the ones that are the same page together. And then we do a mutate. Now, the mutate command works on groups, actually. So I told you originally that when we take the mutate command, it takes each of these as it augments the environment and evaluates your command, such as this line command, with these values set to their columns. So if you've grouped it first, it actually does that several times, and it does it once for each group. So in this case, it's going to take all of page 3 as a group, and then it's going to run. So if we print out enough here, we will actually see. Let's look at 50 lines of headers. we see several pages of headers here. So it's going to run it once with our vector set to this here, and then it's going to run it again with our vector set to this here. So it basically does a whole bunch of subsets of your data and evaluates just on those vectors. So then what I'm doing is I'm saying the line is the cumulative sum where we look at the y1 value. So where's my y1 value here? Here they are. This y1 value and the previous value, so lag by y1. So I look at the difference between these two values, and if it's greater than 4, then I output a true value. So basically, I'll have like false, 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 and then this one here has a jump between 15 and 16. Well, that doesn't have a jump that's big enough. So those will still all be true, true, true. Oh, here's one that'll jump. So between 15.6 and 33.1, that's a spacing of greater than 4 points. So then this will be true. So basically this becomes this, we add a new column here called line, and line is false until you get a jump that's sufficiently large to start a new line, and then it's true, and then it remains false again here. So let's actually just run this, and I'm going to break it up for you. So we can easily break this into components. And I'm not going to actually do the cumulative sum first here. We'll just evaluate it without the cumulative sum. And then you can get the idea here. So there is no initial lag value. There is no previous value for the first line. So then it would normally say an NA there because it says there's no value. But I've provided the true parameter as the default to replace that NA value. And by doing that, I change my first line to true because it starts a line. And then let's print some more lines here. Print n equals, let's get out 50 lines again here. I'll just rerun that. And here you can see, so first line, there was no previous lag value, so that is an NA. We've replaced that NA with true, so that marks the start of a line. And we go down here, and here we are 16.2 to 32.7. That is more than a 4 gap, so we call that true. And where is that over here? I mean, we can look at our stuff here. 205. Yeah, so it's getting the gap between this here and aerodrome facility directory, I believe. So we're looking at, obviously we have some lines that qualify that. We have that a sufficiently large gap. Here, and of course here as well. Anyway, so these gets these columns of true and false values. And then how do we actually turn them into line numbers? Well, that's where the cumulative sum comes in. So true in R is 1 and false is 0. So if we do a cumulative sum starting at 0, we add true to it. So that's 1, that's 1. We add false, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Add 1, we jump to 2. 2, 2, 2, 2, 2, jump to 3. 3, 3, 3, 3, 3, 3, 3. So if we throw in the cumulative sum on top of this here, it will assign those all to line numbers. And then we got the jump here to line number 2 on aerodrome facility directory. And then Ontario actually must be slightly lower due to the big font, so it comes next over here. And then we jump to a new page here, which of course, because we group by page, restarts this procedure, and then we do the same on page 4. So we start on line 1, and so on and so forth. So basically we've classified this information in the headers by their lines now. Let me just put this back to the nice text there. Oops. So then the other thing we wanted to do was some bits on the line, there's clearly large amounts of space between them. So now we arranged the page here by our page and the line number, and then the first starting position of each word. That's what this arrange statement does. And then we group each page and line together, and we look for any time that the the start of the word relative to the next start of the word is greater than 2 times the height of the word. So if we have a space that is greater than twice the height of the word, then we consider it to be a new block of text. And that will just separate out, that'll detect these big gaps here and separate out those values here. So there we're detecting big gaps like this one here. So we'll separate out this text. That's not 2 times, so that'll probably just all be together there. But definitely you have a more than 2 time gap between these 2 bits of text. So that'll separate those out. So let's run the whole command now, and we can see here. Let's print headers n equals 50. We now have lines, and we have chunks of lines as well. Columns would have been a better name, but you can see now it's got Ontario and Ontario here, and the Aerodrome facility directory are the same line, but it's recognized that Ontario is a separate column from the Aerodrome facility directory portion. So now we've broken up the headers into their parts. We got the first line, and then we have the second line with 2 chunks, which are really columns, is what I meant to say, but that's not what I said. So a whole bunch of new stuff in there. We got arrange, which is you can use to order your rows. You have group by, which groups the rows. You have replace NA, which replaces NA values. So R has all its data formats have an option, basically a null option. So missing data, because it's so common in statistics, has a special representation for them, NA. And we have the leg, which shifts a vector forward. So I'll just show you quickly how leg actually works. So if we got leg and say we have C1, 2, 3, what that does is it says, well, on the first position, there was no previous value here, so that's NA. When we're in the second position, the previous value is 1. When we're in the third position, the previous value was 2. So unintuitively maybe a bit, but it makes sense when you actually go through it. Leg shifts your values forward, and it throws in a missing value on the front. We'll come across lead is the other one, which shifts them backwards. In these commands, you can specify how many to shift them by and so far. So basically this does 2 vector subtractions, y1 minus y1 shifted down. All right. So now we're still all working with rows in here, but we've got our words, individual words sorted out into their regions in our headers. So now we want to coalesce the header words into their line chunks. So basically just join the words together is what I'm trying to say there. And that's pretty easy. So we group it by the page, the line, and the chunk. And then here's our summarize command. And what summarize does is it's a reduction operation. So when I said the group by, if you remember, shrinks down those vectors. So if we go have a look at our headers input here again. We've grouped it by the page. So every time page and the line and the chunk. So actually all the stuff printed on this first here, we need obviously to print out more. Let's just do 20. Yes. So if we look at it, this stuff here will all be grouped together because it has the same page, the same line, and the same chunk. So the vector operations will work on these vectors. So y1 will be to here, and then the next y, and then it'll do the same operation again on just this line because it's the only one with that one, and then it'll repeat the operation on this line. Well, there's more to this line. Yes, I'm missing the word directory, so there's actually one more line to that line. So summarize passes in these, and it expects you to reduce those vectors to a single value. So how do we do that? Well, we take the text and we hit it with string flatten being another stringr command, which just converts a vector of strings to a scalar by concatenating them all together. So it'll just take Canada, flight, supplement, blah, blah, blah. It'll squash those all down, separating them with spaces. And then we want to also preserve our X, Y, and our bounding box information. And that's pretty easy. If you've got a bunch of boxes, the global bounding box, the left-hand side is the minimum of the left-hand sides, the right-hand side is the maximum of the right-hand side. So you can just collapse that into a bigger bounding box. And then we should be good to go. So let's give that a go. Have a look at what our headers look like now. And you can see now we've got the Canadian Flight Supplement stuff on line 1. We have Ontario and Aerodrome Facility Directory on line 2. And it's recognized that Ontario and Aerodrome Facility Directory are actually separate chunks of text or separate columns. There we go. So we've now pulled the headers together into something that's useful to us. And what we can do with that is we can say, okay, well, if the last line of text is Aerodrome Facility Directory, then that's the page we want. So we're going to group them by page, and then we're going to filter on the last of the text values. So that'll be, go back to what we've got here. So we group them by page. So here, these guys are all on the same page. And then if the last entry is Aerodrome Facilities Directory in that vector, so last takes a vector and extracts them, then we keep it. Otherwise, we throw it out. And then we pump it through summarize, which is supposed to reduce these down to values, but we don't tell it. We don't actually want any summary data out of it. So after we're done, the only thing we'll be left with is the grouping variables. So of course, the grouping variables are constant within a group. By definition, like the page here, we group by page. So everywhere a group is defined as page is constant. So those survive summary operations. Nothing else survives summary operations unless you provide a redefinition like I did in here that tells it how to compute the new text from the old text or the new X0 from the old X0. And it doesn't have to be the new from the old. It can be an entirely, I could call this line equals string flattened text if I wanted to, right? I can give them new names. But basically all the old variables that weren't grouping variables are gone, and the only variables you're left with are the grouping variables and the new ones you've assigned in the summarize. So let's give that a run there. Basically, we expect to see page 3, page 4, page 5, and so on. Oops. We'll run this through pages. And indeed, it has extracted the pages. And then you can see there's 480 rows, so we can see it has dropped off the a huge proportion of the last pages there. I'm just going to bring this back across so we have a little more space to look at the columns there. So last just takes the last value out of a vector. So that's the only sort of new item there. And then basically we take our input, we pull off all the pages we have. Now you don't actually have to do that because this is the pages is, well, sorry, we want to, so we take semi-join is the opposite of anti-join. So anti-join, remember, removed the stuff on the left that was already in the stuff on the right. Semi-join keeps the stuff on the left that's also on the right. So this says, okay, now our input, keep the ones that matches up with pages. Pages has one row to it that gives the page. Input has a row also called page. So it's going to match these together. And every time it finds a match between this page and that page, it's going to keep that line. Otherwise, it's going to throw them all away. So we do that. So we pull all the pages we are interested out of input and assign them to pages. And then we go through input and we pull away all the pages we've kept. So input is basically our unprocessed data. And I actually found it very useful to keep track of the unprocessed data because that let me catch a lot of mistakes. I would look at it and I'd be like, huh, why is that still there? How did I miss that, right? Because we're looking at 455 pages of data. So to be able to separate it out into your two sets is very useful. Anyways, let's do that. Pages, input. Now, if we look at our pages, we can see it's just this section here. Strangely enough, it starts with ONCPE2, which we don't find anywhere on the page. But if you actually search for it, it's there. It's in white text in this upper left-hand corner. They have the name, the international code for the aerodome CPE2, which is also over here, and they've prefixed it with the provincial code for some reason. So that's hidden in each page in the upper left-hand corner right here. So we'll have to deal with that. So again, there's another example of, stuff that comes up that makes data wrangling nasty. So now to identify our actual aerodomes, this particular documentation has each aerodome is its own page or sections of pages, but there are other samples that have more than one on the same page. So you'll have like Ajax Pickering, and then if there's enough space, they'll stick another one right underneath here. So we want to break out each aerodome. And fortunately, the aerodomes have their own nice header themselves. So that, of course, is right across the top here. So we want to recognize this header. So we just do the same sort of trick. We turn the whole page into lines and columns, or lines and chunks, as I've called them. And then when we have the whole page in lines and chunks, we can just look for a line that has two chunks, so two columns, and then the right-hand column is in the form of C for Canada, and then 3 letters to identify the aerodome. So nothing to this. We've seen this already, the paging into lines and chunks. So we'll hit that with the pages. You can see, I mean, this is quite a bit of data. That was 60,000 rows of data. And our powered to these are very fast commands. So here we are, we've got the lines and chunks, and then we've assigned them the numbers. So we arrange them and we flatten the strings and we recalculate the bounding boxes. Nothing new here at all. And we get lines, which is each page done up by lines. So we have these mysterious ones here, which I said are floating up in the upper left, ONCEPT, but now it's got Ajax Pickering General Hospital. And then on the right, it's got the CPE2, and then it's got these broken up here. I mean, it won't have done a decent job. These like this, it'll recognize as separate columns, but probably there's a chance on some of these that it'll actually amalgamate these right-hand labels with the text on the right-hand side. But this is enough for us to extract the aerodome codes, which is exactly what this code does. So X0, so the left-hand margin here identified as 27 points. The right-hand margin identified as 37 points. And then what I want is a bit of text where the left-hand, where that has 2 chunks, 2 columns to it. And so the left-hand column should start at 27. The right-hand column should end at 337 or thereabouts. And the right-hand side should be in this format. So this is a regular expression. So the start of it should be C, and then it has either a number 0 to 9 or letters A through Z repeated 3 times, and then that should be the end of the string. So just this, that's what they call a regular expression. And so that's what this does. Now, there is some new stuff in here. So there's the pivot wider command. So let's talk about what pivot wider does. So first of all, let's have a look at our aerodomes table. Sorry, aerodomes is from our lines table. Let's have a look at our lines table. So our lines table has chunk numbers. 1, 1, 2. And what we want to deal is we want to work on, I said I want to see the left-hand side here is in the right-hand side here. But that information is on separate rows because if we look at it here, this here is one row in our lines table because it's one column, and this here is a separate row. So we want to combine those two rows into one row so we can process on it. And the way we're doing that is this pivot wider command. And what the pivot wider command will do, here we go. So I tell it the names to pivot from are from the chunk column, and the values are from text x0, x1, xy, x0, and so on. So it looks at the ones I have defined. So I'm going to say, okay, you get the values from these columns here and the chunk and the text, sorry, the text x0, xy, x0, and then the chunk becomes your names. So it's going to group everything by page line. So everything I haven't mentioned gets grouped by. So these here too, let's see, for example, these two have the same page and line, so they will become one row. And what that row is going to have is it's going to have a name prefix called chunk. So it's going to be chunk and then the value, so chunk 1. It will be the name of it. Chunk 1 text will be this. Chunk 2 text will be CPE2. So it takes these rows and then it basically sets them adjacent to each other and then joins them together. I guess that's probably the easiest way to say it. So you take your rows, you put them, your individual rows, you make all on one big new row, and then that's what you're left with. I think it'll become clearer here if I actually run the code. So we'll just define those cut points there. And then we'll just see what this pivot wider does. So this was my lines initially. And then when I hit it with pivot wider, this is what I'm left with. So let's just make this a little bit bigger so we can see here. Yes. So as I had mentioned here, this one here is the only unique is this guy here has page and line is unique to it. So it just survives itself and it's created all these new columns without values. This guy here, Ajax Pickering, and well, that's unique as well. And sorry, I'm looking at here's my row, my page and my line. These are just the row numbers off on the left-hand side. Yes, so Ajax, Pickering, and CPE2, these here become one row. And then because there's two different values of chunks, it'll have created two columns. So text chunk 2 will be from the text where chunk was 2. There's also be a text chunk 1 in here. If we scroll across, the ordering of them is bad. Text chunk 3, text chunk 1, here it is, yeah. So text chunk 1 will be where chunk was 1. So that'll be Ajax Pickering. Text chunk 2 will be where chunk was 2. So that's CPE2. Now there were ones with actually a third block of chunk of text. This one didn't have any, that's why that survived. Now x0 chunk 1 will be the x0 value here where chunk was 1. x0 chunk 2. So you can see basically it took those two lines, it used the value of chunk along with the prefix I gave it to prefix. Actually, I don't know why they call it prefix because it's basically suffixed them all. Suffixed all the columns to uniquely identify them and then gave me a new table. So it brought all those rows up together into one row and then it just basically gave new names to all the columns so there was no conflicts. And now I have text chunk 1 and text chunk 2 on one row. So I have taken all my lines and I have put all my lines, the individual columns or chunks as I'm calling them, onto one row, which then lets me do my sort of operations I want on them. In this case, the operation I want us to see is the x0 chunk 1 near the aerodome side here on the left-hand side, and is the x1 chunk 2 near the far right-hand side, and is the text for chunk 2 in this format where it starts with C and then it's got 3 letters. If it is, then it's the line I'm interested in. It's one of these header lines. So I can record mutate page. If I just specify the variable, that's page equals page. So that does nothing. And then I reassign text chunk 1 to the name. I reassign the aerodome to text chunk 2. So text chunk 1 becomes the name of the aerodome. Text chunk 2 is the aerodome code. So I assign that to aerodome. I assign Y. So I look at the maximum of the bottom of these individual guys here, and I assign that to be the Y value. So I identify where the cut point is across the bottom of this header. And then this dot keep equals none is an option, which means if I didn't mention a variable in my mutate command, I want you to get rid of it. So that just drops off all these other like text chunk 3 and stuff. So let's run that full command, and we can see here exactly what it does. Aerodromes. So that's got it, just like we said. So it says, oh, page 3, line 2, here's the name of the aerodrome, Ajax Pickering, and here is the aerodrome code, and the Y cutoff point here is 54.4. Page 4, it's Alexandria, CNS4. We can scroll down and have a look at that one, and so on and so forth. So we basically pulled out all the aerodromes. Now, it turns out there's some mess involved in there because a bunch of these aerodomes are there's these ones that are aerodrome control centers, which aren't actually places you can land at. They're involved, like there's one in London and stuff. They're involved with operations, with Transport Canada operations, but they've assigned them numbers and stuff. So basically we want to get rid of those. So here's their particular codes. There's not a huge amount. There's one in Winnipeg, one in London, one in Ottawa, and stuff like that. I forgot to talk about this. So we have pivot wider. We did a lot of talking about what pivot wider does. We have near, which is for comparing numeric vectors. You know, if you compare doubles, they don't compare well at all. So the R has given you it because, you know, they might differ in the 12th decimal place by a little bit due to rounding error. So R gives you a near function, which gives you ability to specify two doubles and then a tolerance to compare them to. So I'm considering it to be left hand if it's within 4 points of my aerodome X0. So I don't require, 4 points is 4/72 of an inch, which is pretty tiny. And then we have string detect, which basically just you can use it to detect patterns. You got regular expressions, you got fixed offsets. There's a whole bunch of options for the pattern there. The default's a regular expression. And it just takes this text chunk 2, which is a vector of texts in column 2 for whatever the line happens to be. It compares it to that regular expression and then returns true or false if it matches or not. So that's the full filter line. So now we're going on here. We want to get rid of all these CZEG and so on and so forth. We can actually just see here what that actually looks like. Aerodromes. Now, again, here I can either pipe aerodromes in to provide as the first argument, or I can specify it myself. So we want to say aerodrome equals CZEG. Maybe that's one that is not actually. Yes, there we go. So Toronto Center on page 457. I carry the pages around a lot because, yeah, right. So this is not somewhere you can land on. It's just a bunch of contact information for that control center. So this is the stuff that we want to get rid of out of our thing there. So we're just going to filter those out easily by basically if aerodrome is in this list of area control centers, then we don't want it. And then we're going to ungroup, and then we're going to run this factor command. So the arrow dome are these codes here. They're uniquely defined. So basically, behind the scenes, we're going to turn them into a factor. So we replace them with numbers. And that allows it to, because it's way quicker to compare if a number is the same than a string. So that just speeds up operations a little bit. And then we group them by the arrow dome. And so there's a couple of these. Like if we look for, like, say, Billy Bishop, that are so large, like when you're flying into Toronto, it's several pages. So you'll have Billy Bishop, and then the next page will be like Billy Bishop continued, and then Billy Bishop continued. So we want to just change the name to being the first name to get rid of all those continues. So that's what this does here. We take the name and replace it by the first name. And first, of course, being the complement to last. So we can run these quickly. That's just some cleanup. You don't actually, you won't see it make any difference to the first pages, but that data is in there. All right, so I guess I am out of time here now. So we'll have to call this off here. What can I tell you more about it quickly? It works really well. And yeah, maybe we can do a second talk to get the second part at some point.